Right now, the force holding your entire body against the surface of this spinning planet is roughly a trillion times weaker than the force binding together the atoms inside a single one of your fingertips. To feel how staggering that gap truly is, consider that a small magnet, the kind that holds a child side, with nothing to do and no lectures to attend, Newton spent the plague year simply thinking. And in that single year of enforced isolation, alone in the silence of a farmhouse, he laid the foundations of calculus, of the study of light and colour, and of the theory of gravity that would carry his name for the rest of human history. The story of the apple is, for once, probably true, at least in its outline. Newton himself told the tale in his old age. He was sitting in the garden, the story goes, when he watched an apple fall from a tree. And the question that occurred to him was not why the apple fell. Everyone already knew that apples fell. The question that occurred to him was something far more daring. Why does the apple fall straight down toward the center of the earth, while the moon, hanging there in the sky, does not fall down in the same way? What if, Newton wondered, the moon is also falling? What if the very same force that pulls the apple to the ground also pulls upon the moon, and the moon does not crash into the earth only because it is moving sideways so swiftly that it perpetually misses, falling around the earth in an endless curve rather than falling down onto it? This was the great unification. The force that pulls an apple from a branch, Newton proposed, is the very same force that holds the moon in the sky, the same force that holds the earth in its great path around the sun, the same force that governs the motion of every planet, every comet, and every distant star. One law, reaching from the orchard all the way to the heavens. He called it universal gravitation, and the word universal was the entire point of it. It was not one rule for earthly things and a different rule for celestial things, as the ancients had always believed. It was a single rule, the same everywhere, binding the smallest pebble to the largest of worlds. Newton wrote the law down in mathematical form, and it is worth describing in plain language, because its very structure holds the answer to our question. The gravitational pull between any two objects, Newton found, depends upon just two things. It depends on how much mass each object has, multiplied together, so that more massive objects pull harder upon one another, and it depends on the distance between them, growing weaker as they move apart, and weaker not in simple proportion, but in proportion to the square of the distance. Double the distance between two objects, and the pull drops to 1/4 of its former strength. Triple the distance, and the pull drops to 1/9. This is the famous inverse square law, and it describes the long reach of gravity across all of space. Now, here is the detail that matters most for everything that follows, and it is so easy to overlook that almost everyone walks right past it. In Newton's equation, the masses are always positive. There is a number for the overall strength of gravity, and there are the two masses, and there is the distance between them, and when you put all of those together, the force you calculate always points the very same way. It always pulls the two objects toward each other. There is no arrangement of ordinary masses, no clever configuration anyone has ever devised, that can make the equation produce a push instead of a pull. The mathematics simply does not allow it. Compare this with the equation for the electric force, which was written down in the following century and looks almost identical in its structure, but with one crucial difference. In the electric equation, the charges can be positive or negative, and when you multiply a positive charge by a negative charge, you get a negative result. And that negative result flips the direction of the force from a pull into a push. Electricity has a minus sign available to it. Gravity does not. Mass comes in only one flavour, and that single flavour can only ever attract. Newton's law was not merely elegant. It was breathtakingly, almost frighteningly accurate. It predicted the motions of all the planets. It explained the rise and fall of the tides as the pull of the moon and the sun upon the oceans of the earth. And in one of the great triumphs of the entire human mind, it predicted the return of a comet. Newton's friend, the astronomer Edmund Halley, used the new theory to calculate the path of a comet that had appeared in the year 1682, and he predicted that the very same comet would return roughly 76 years later. Halley did not live long enough to see it for himself, but on Christmas night in the year 1758, exactly as the mathematics had foretold, the comet appeared once again in the sky. A dead astronomer had reached across the decades and told the living world precisely when a wandering light would return. That is the kind of power Newton's law had unleashed upon the world. Yet for all of its power, there remained one number that Newton himself could not pin down, and one question that he refused even to attempt. The number was the strength of gravity itself, the constant that tells you exactly how strong the pull will be between two given masses. Newton knew the shape of the law, but he could not measure that constant, because gravity is so absurdly weak that the pull between two ordinary objects on a tabletop is almost impossibly faint. To measure it, you would need an instrument sensitive enough to detect the gentle attraction between two simple lumps of metal sitting quietly in a room, a force smaller than the weight of a single grain of sand. That instrument was finally built more than a century later, in the year 1798, by a reclusive English scientist named Henry Cavendish. Cavendish was one of the strangest figures in the whole history of science, a man of enormous inherited wealth and crippling personal shyness, who spoke so rarely that some who knew him claimed they had heard his voice perhaps only once or twice in their entire lives. He communicated with his own household servants by leaving written notes for them, and in the privacy of his laboratory, this profoundly isolated man performed one of the most exquisite measurements ever attempted by anyone. He suspended a slender rod with a small lead ball fixed at each end from a thin and delicate fibre, so that the rod could twist freely in either direction. Then he brought two large and heavy lead spheres close to the small ones. The faint gravitational pull between the large spheres and the small ones caused the rod to twist by a tiny, almost invisible amount, and by carefully measuring that gentle twist, Cavendish measured the strength of gravity itself. The experiment was so delicate that the warmth of his own body, or the faint stirring of air in the room, could ruin it entirely, and so he watched it from a separate room through a telescope, to avoid disturbing the apparatus with his own presence. Newspapers of the time described his work as weighing the world, because once you know the strength of gravity, you can calculate the mass of the entire Earth. A painfully shy man in a quiet room had weighed the whole planet by watching a single thread gently turn, and still, after Aristotle and Galileo and Newton and Cavendish, after 2,000 years of patient thought, and one of the most successful scientific theories ever devised by anyone, the deepest question remained completely and stubbornly unanswered. Newton could tell you exactly how strong the pull would be between any two objects anywhere in the cosmos. He could predict eclipses and comets and the slow stately dance of the planets, but he could not tell you what gravity actually was. He could not say how one object reaches across the empty void of space and tugs upon another that it is not even touching. The idea that the sun could pull upon the Earth across 93 million miles of nothing at all, with no rope, no contact, and no visible mechanism, troubled Newton deeply for the whole of his life. He called such action at a distance an absurdity, and he honestly refused to pretend that he understood it. In one famous line, he wrote that he would feign no hypotheses, meaning that he would not invent a comforting story to explain a thing he could not truly explain. He had described gravity with perfect precision, and admitted, with a rare and admirable honesty, that he had no idea what it was. So here is the crushing truth that stood at the end of those 2 long centuries. The most accurate theory that humanity had ever produced could predict the pull of gravity to a precision bordering on the miraculous, and yet it could not answer the 2 simplest questions that a curious child might think to ask. What is this force really? And why, alone among all the forces in nature, does it only ever pull? The answer to both of those questions would not arrive from a farmhouse or a quiet laboratory. It would arrive from the mind of a young patent clerk in Switzerland, and it would require us to abandon, entirely and forever, the comfortable idea that gravity is a force at all. So if Newton could not say why gravity only pulls, where do we even begin to look for an answer? We begin, strangely enough, by looking closely at a force that does the very opposite of what gravity does. A force that pushes just as easily as it pulls. We begin with electricity, because the contrast between electricity and gravity is the single clearest window into why gravity behaves the way it does. And understanding that contrast is the first real step toward understanding the one-way pull. The two forces look almost like twins on paper. They follow the same kind of mathematical law, fading away with the square of the distance, and yet one of them can shove things apart, while the other can only ever draw things together. Everything depends on a single difference, and that single difference is everything. The story of electric charge begins with a printer and statesman in colonial America named Benjamin Franklin, working in the middle of the 18th century. Franklin studied the strange crackling phenomenon of static electricity, the same force that lifts the hair on your arm or snaps at your fingertip on a dry winter day. He realized that this electrical influence came in two opposing kinds, and he gave them the names we still use today. He called one kind positive and the other kind negative. The choice of which to call positive was, as it happens, entirely arbitrary, and Franklin guessed wrong about which way the charge actually flows. A mistake we are still politely living with centuries later. But the deep insight was correct, and it changed everything. Electricity comes in two opposite flavors, and those two flavors behave toward one another in a very particular way. Two positive charges push each other apart. Two negative charges also push each other apart. But a positive charge and a negative charge pull toward one another, like repels like. Opposites attract. This is the rule that governs the entire electric world. Now hold that rule in your mind, because it explains something you experience every waking moment without ever noticing it. You are made of an enormous number of electric charges. Every atom in your body contains a dense central nucleus carrying positive charge, surrounded by a cloud of negatively charged electrons. The electric force between these charges is monstrously, almost unbelievably strong, far stronger than gravity by those many factors we spoke of at the very beginning. So why do you not feel it tearing you apart or slamming you against the nearest wall? Why does the electric force, so overwhelmingly powerful, seem to play almost no role in your daily life? The answer is the heart of the whole matter. In ordinary matter, the positive and the negative charges come in almost perfectly equal amounts, and so they cancel each other out. Every positive nucleus is balanced by its negative electrons. The pushes and the pulls add up to very nearly nothing. From a small distance away, a chunk of ordinary matter looks electrically neutral, its tremendous internal forces folded up and hidden, locked in a quiet truce that hides their strength. This is the great secret of why the strongest of forces hides itself away. Electricity cancels, because it comes in two opposing signs. The positive and the negative arrange themselves into balance, and their enormous strength is mostly neutralized on any scale larger than a single atom. The most powerful everyday force in the universe spends most of its time hiding inside a perfect and silent equilibrium. And now we arrive at the answer to the riddle that opened this entire journey. The riddle of how the weakest force could possibly rule the cosmos. Gravity does not cancel. It cannot cancel, because it comes in only one sign. There is no negative mass to balance positive mass the way negative charge balances positive charge. Every speck of matter in the universe carries the same gravitational sign, and so every speck of matter pulls in the same direction, toward every other speck. The pulls never cancel, they only ever add. Take a single atom, and its gravity is laughably, unmeasurably weak. But take a planet's worth of atoms, every one of them pulling in the same direction, with no opposing push to neutralize it, and those countless feeble pulls accumulate into a force strong enough to hold you to the ground and hold the moon in the sky. The electric forces inside that same planet, vastly stronger atom for atom, have almost entirely cancelled themselves out, leaving the field clear for the weakest force to win by sheer relentless accumulation. This is the deepest reason gravity governs the large-scale universe. Not because it is strong, it is pitifully weak, but because it never cancels, and so given enough matter and enough time, it always wins. Consider what this means. The reason gravity shapes galaxies while electricity shapes only atoms is not a question of raw power, it is a question of cancellation. Strength that cancels itself out is, on the largest scales, no strength at all. Weakness that never cancels is, on the largest scales, the master of everything. The universe is built not by the mightiest force, but by the most patient one. The one force that always adds and never subtracts. So the real question sharpens into something far more precise. The question is no longer simply why gravity pulls. The question is why there is no negative mass. If a kind of mass existed that carried the opposite gravitational sign, then gravity too would push and pull, it too would cancel out, and the cosmos would be a profoundly different and emptier place. So we must ask, has anyone ever found negative mass? Has any object, anywhere, ever been observed to fall upward, to be pushed away by the Earth rather than pulled toward it? And the honest answer, after centuries of looking, is no. Not once. Every object ever measured, every particle ever detected, every form of matter and energy ever studied, carries positive mass and positive energy. The great equation that connects mass and energy, the one written down by Einstein, tells us that mass is simply a concentrated form of energy, and the energy of every known thing is positive. There is, as far as anyone has ever been able to find, no such thing as negative mass in the ordinary universe. The minus sign that electricity enjoys is simply not available to gravity, and without that minus sign, gravity is condemned to pull, and only pull, forever. This single fact, the one-sidedness of mass, has a consequence so strange that it is worth pausing on, because it reveals just how different gravity truly is from every other force. You can shield yourself from electricity. This was discovered by the great English experimenter Michael Faraday, working in London in the 1830s. Faraday built a room lined with metal foil and sat inside it while powerful electric charges crackled across its outer surface. Inside the room, his instruments detected nothing at all. The charges in the metal had rearranged themselves to perfectly cancel the field within, leaving a pocket of complete electrical calm in the middle of an electrical storm. This is why you are safe inside a car during a lightning strike, and why a metal enclosure can protect sensitive equipment from interference. The trick works precisely because electricity has two signs. The charges in the metal shuffle around, positive moving one way and negative the other, until they exactly oppose and cancel the outside field. You can build a shelter from electricity because electricity can be cancelled. You cannot do this with gravity. There is no such thing as a gravity shield, and there never can be, for the deepest of reasons. To cancel a gravitational field, you would need negative mass to rearrange itself the way charges rearrange themselves in Faraday's metal room. But there is no negative mass. There is nothing in the universe that responds to gravity by pushing back against it, and so there is no material, no clever device, no enclosure of any kind that can shield you from gravity. You can hide from electricity inside a metal box. You can hide from light behind a wall. You can hide from sound inside a sealed chamber. You cannot hide from gravity anywhere in the universe. It passes through everything. It reaches into every room, every cave, every sealed vault buried deep beneath the Earth. The pull of every distant galaxy is reaching you right now, faint beyond measure but utterly unstoppable, and there is no wall thick enough, and no shelter deep enough to block even the smallest fraction of it. This is the unsettling reality of a one-way force. Every form of protection we know works by opposition, by setting one thing against another, by cancelling a push with a pull or a pull with a push. But gravity offers nothing to oppose. It is a pull with no answering push anywhere in nature. a force you can fall toward but never be sheltered from. The walls of your room are filled with atoms whose electric forces hold them rigid and keep you from sinking through the floor. But those very same walls do absolutely nothing to weaken the gravity passing through them. You live your whole life inside a field that nothing can block, generated by every particle of matter that has ever existed. All of it pulling, none of it pushing, none of it cancelling, all of it reaching for you across the dark. And the only reason you do not fall endlessly toward the center of the earth is that the ground, with its rigid electric forces, pushes up against your feet and holds you in place. You are not resting, you are being held by one force against the relentless pull of another. And yet even now, with all of this understood, we still have not reached the deepest answer. We have learned that gravity pulls because mass comes in only one sign, and that it cannot be shielded because there is no opposite to cancel it. But this only pushes the mystery one level down. Why should mass come in only one sign? Why should energy always be positive? What is it about the underlying nature of gravity that forbids the very existence of a repulsive version? To answer that, we have to leave Newton behind entirely, and we have to stop thinking of gravity as a force at all. Because the man who finally explained what gravity really is did not describe a force reaching across space. He described something far stranger and far more beautiful. He described the bending of space and time themselves. The man was Albert Einstein, and in the year 1905 he was not yet a professor, not yet famous, not yet the white-haired icon the world would later know. He was a junior clerk in a patent office in the Swiss city of Bern, examining applications for inventions during the day and quietly rewriting the foundations of physics in his spare hours. In that single extraordinary year, sometimes called his miracle year, he published a handful of papers that transformed our understanding of light, of atoms, of energy, and of space and time. But the work that would finally explain gravity took him another full decade of struggle, and it grew from a single thought that came to him while sitting at his desk, a thought he later called the happiest thought of his entire life. The thought was this: imagine a man falling freely from the roof of a building. While he is falling, Einstein realized the man feels no gravity at all. He feels weightless. If he were to release a ball or a set of keys beside him, they would not fall away from him, because they are falling at exactly the same rate that he is. From his point of view, floating beside his own keys, gravity has simply vanished. This is the same weightlessness that astronauts feel aboard a spacecraft orbiting the Earth. They are not beyond the reach of gravity. Gravity is what holds them in orbit. They are weightless because they are falling, perpetually and freely, the same way Newton's moon falls around the Earth without ever landing. Falling cancels the feeling of gravity completely. Einstein took this simple observation and turned it into one of the most powerful principles in all of physics. He called it the equivalence principle. It says that there is no difference, none whatsoever, between the pull of gravity and the push of acceleration. Imagine you are sealed inside a windowless room with no way to look outside. The room could be sitting still on the surface of the Earth, with gravity pulling you down to the floor, or the room could be far out in empty space, with no gravity anywhere nearby, but accelerating upward, the floor rushing up to meet you so that you are pressed against it just as firmly. Einstein realized that no experiment you could perform inside that sealed room could ever tell you which situation you were in. Gravity and acceleration are not merely similar, they are, in the deepest sense, the very same thing. And if gravity is the same as acceleration, then gravity is not really a force pulling on objects at all. It is something about the shape of the path that objects naturally follow through the world. To turn this insight into a complete theory took Einstein 10 years of the hardest thinking of his life, and the result, published in the year 1915, was the general theory of relativity. It is widely regarded as the most beautiful theory in the history of physics, and its central idea can be stated in a single breathtaking sentence. Gravity is not a force. Gravity is the curvature of space and time. Matter and energy bend the spacetime around them, and other objects moving through that bent spacetime follow the straightest possible paths available to them, which to us, watching from the outside, look like the curving arcs of falling and orbiting. The physicist John Wheeler summarized the whole theory in a phrase that has never been improved upon. Matter tells spacetime how to curve. Spacetime tells matter how to move. This is a profoundly difficult thing to picture, and the usual way people try to picture it is with a stretched rubber sheet. Imagine a taut rubber sheet, like a trampoline, pulled flat. Now place a heavy bowling ball in the center. The sheet sags downward, forming a dip around the ball. Then roll a small marble across the sheet, and instead of traveling in a straight line, it curves toward the dip, circling the heavy ball or spiraling inward toward it. The heavy ball has not reached out and grabbed the marble. It has simply bent the surface the marble is rolling on, and the marble, doing nothing but rolling forward, follows the curve. This is how mass curves spacetime, and how that curvature guides the motion of everything around it. The Earth does not reach up and pull the Moon. The Earth bends the spacetime around it, and the Moon simply rolls along the resulting curve, falling endlessly around the dip in a path it cannot help but follow. The rubber sheet is a useful picture, but it is also deeply misleading, and it is worth understanding why, because the truth is even stranger. The rubber sheet only works as an analogy because we are watching it from above, with real gravity pulling the bowling ball down and making the dip. It secretly uses gravity to explain gravity, which is circular and not really an explanation at all. The deeper truth is that it is not mainly space that bends to create the gravity you feel every day. It is mostly time. This is the part that almost no popular picture captures. The reason an apple falls toward the Earth is not chiefly that space is dented beneath it. It is that time itself runs at very slightly different rates at different heights, running ever so slightly slower closer to the Earth, and an object at rest in this warped flow of time naturally drifts toward where time passes more slowly. The falling of the apple is, in a sense, the apple following the gradient of time. This sounds almost impossible to believe, and yet it has been measured directly, and the measurement is one of the most astonishing in the history of science. Before we reach that measurement, though, the new theory faced its first great test, and the test came from light. Einstein's theory made a bold prediction. If mass bends spacetime, then the path of light itself should bend as it passes near a massive object, because the light is traveling through curved spacetime just like everything else. Newton's older theory predicted a tiny bit of bending too, but Einstein's theory predicted exactly twice as much. Here was a way to decide between the two. The trouble was that the only object massive enough nearby to test this was the Sun, and you cannot see stars near the Sun because the Sun is far too bright. Unless, that is, the Sun is blotted out by a total eclipse. In 1919, the English astronomer Arthur Eddington led an expedition to test Einstein's prediction during a total solar eclipse. Eddington travelled to the remote island of Príncipe off the west coast of Africa, while another team set out for the town of Sobral in Brazil. As the moon slid across the face of the Sun and day turned briefly to an eerie twilight, the astronomers photographed the stars that appeared near the darkened Sun's edge. Then they compared the positions of those stars with their normal positions in the night sky months earlier. If Einstein was right, the starlight would be bent as it grazed the Sun, and the stars would appear slightly shifted out of place. The measurement was difficult, and the conditions were poor, with clouds threatening to ruin everything. But when the photographs were finally analysed, the stars had shifted by exactly the amount Einstein had predicted, twice the Newtonian value. Light itself was bending around the Sun. When the result was announced, Einstein became almost overnight the most famous scientist on Earth, his name carried in newspaper headlines around the world. A patent clerk's strange idea about the bending of spacetime had reached up and rearranged the apparent positions of the stars, and reality had agreed with him. But the bending of starlight, however dramatic, was only the beginning. The strangest prediction of all concerned time itself, and it brings us back to that astonishing measurement. If gravity is the warping of time, then a clock deep in a gravitational field, closer to a massive object, should tick more slowly than a clock farther away. Not because the clock is broken or running poorly, but because time itself genuinely passes more slowly there. This effect is called gravitational time dilation, and it sounds like pure fantasy. Yet in 1959, two physicists at Harvard University, named Robert Pound and Glenn Rebka, set out to measure it inside a single building. They sent a beam of light up a tower roughly 74 feet tall from the basement to the roof and measured the incredibly tiny change in the light's energy as it climbed up out of the Earth's gravity. The change was unimaginably small, a shift of a few parts in 1,000 trillion, and yet their apparatus was sensitive enough to detect it. Time really did run more slowly at the bottom of the tower than at the top. The difference was minuscule, but it was real, and it was exactly what Einstein's equations demanded. A little more than a decade later, in 1971, two more scientists named Joseph Hafele and Richard Keating pushed the experiment around the entire world. They placed extremely precise atomic clocks aboard ordinary commercial airliners and flew them around the globe, then compared them with identical clocks that had stayed on the ground. When the travelling clocks returned, they disagreed with the stationary ones by tiny fractions of a second, in precisely the way that Einstein's theory predicted, accounting for both their speed and their altitude. Today this is not some delicate laboratory curiosity. It is a daily engineering reality. The satellites that allow your phone to find its position on a map orbit high above the Earth, where time runs measurably faster than it does on the ground. If engineers did not constantly correct for this difference, the navigation system would drift off by several miles within a single day, and your maps would become useless. Every time a device finds your location, it is silently accounting for the warping of time predicted by a patent clerk over a century ago. Consider what this truly means for you, right now, sitting where you are. Your head is slightly farther from the center of the Earth than your feet, and so, by an unimaginably small amount, time is passing more quickly at your head than at your feet. Over an entire human lifetime, the difference adds up to a few billionths of a second, far too small to ever notice. But it is real. Your head genuinely ages faster than your feet. You are not a single object moving through a single uniform time. You are a tall creature stretched across a tiny gradient of warped time, your upper half racing infinitesimally ahead of your lower half, every second of every day. This is the world Einstein revealed. Not a stage on which forces push and pull, but a flowing, bending fabric of space and time, shaped by everything that has mass, guiding everything that moves. And now we can finally see, at least in outline, why gravity bends only one way. Mass and energy curve space-time, and because mass and energy are always positive, they always curve it in the same sense, creating those dips and slopes down which everything naturally falls. There is no negative mass to curve space-time the opposite way, to push up a hill instead of carving down a valley. So objects fall together, always, drawn down the slopes that positive matter creates. The pull is not a pull at all. It is the shape of a valley that only ever opens downward. But here, hidden inside the very equations Einstein wrote, lies a loophole so profound that it overturns the simple story we have been telling. Because it is not only mass that bends space-time. Einstein's equations say that energy bends it, and motion bends it, and pressure bends it too. And once pressure can bend space-time, the door swings open to something almost no one expected. The door swings open to the possibility that gravity, under the right conditions, can push. To understand how gravity could ever push, we have to look more carefully at what actually sits inside Einstein's equations as the source of gravity. In Newton's old theory, the source of gravity was simple. It was mass, and only mass. The more mass an object had, the more strongly it pulled. But Einstein's theory is richer and stranger than that. In general relativity, the thing that bends space-time is not mass alone. It is a whole bundle of related quantities woven together, including energy, including momentum, and, most surprisingly of all, including pressure. Pressure, the very thing that makes a balloon firm or a deep ocean crush a submarine, is itself a source of gravity. This sounds almost absurd at first. We think of pressure as something that pushes outward, that resists compression, that holds things up against being squeezed. How could pressure possibly add to gravity? And yet the equations are unambiguous. Pressure gravitates. The harder a thing pushes outward internally, the more it bends the spacetime around it, and the more it gravitates. For ordinary objects, this contribution is far too small to notice, because the pressures involved are tiny compared with the energy locked up in their mass. The pressure inside a rock, a planet, even an ordinary star, adds only the faintest whisper to its gravity. So in everyday life, and even in most of astronomy, you can safely ignore it, and gravity behaves exactly as Newton said, pulling and only pulling. But the equations contain a hidden possibility, a loophole that ordinary matter never opens. The contribution of pressure to gravity is positive when the pressure is positive, the normal outward kind of pressure. But the mathematics works just as well for negative pressure, for a kind of inward tension rather than an outward push. And here is the strange and crucial point. Negative pressure makes a negative contribution to gravity. Negative pressure, in other words, repels. If you could fill a region of space with something that had a strong enough negative pressure, that region would not pull things in, it would push them apart. Gravity itself would reverse. This is so important and so counterintuitive that it is worth saying again, slowly, in the plainest possible terms. In Einstein's universe, gravity does not respond only to how much stuff is present. It responds to the pressure of that stuff as well. Ordinary matter and ordinary energy always pull, but a substance with negative pressure, a kind of cosmic tension stretched through the vacuum, would push. The gravity of negative pressure is repulsive. And the moment physicists understood this, decades ago, a quiet question began to take shape in the back of their minds. Is there anything in the real universe that has negative pressure? Is there anything out there, in the vast dark between the galaxies, that gravity pushes rather than pulls? For most of the 20th century, the answer seemed to be no. And then, near the very end of that century, the answer turned out to be a resounding and terrifying yes. The first person to seriously entertain repulsive gravity was, fittingly, Einstein himself, and the story of how he did it is one of the great cautionary tales in science. In the year 1917, just 2 years after he completed general relativity, Einstein turned his new theory toward the largest possible question: the structure and fate of the entire universe. When he wrote down his equations for the cosmos as a whole, he discovered something that deeply troubled him. The equations refused to allow a static, unchanging universe. Because all matter attracts all other matter, a universe full of galaxies should be pulling itself together, collapsing inward under its own gravity. Yet the universe, as everyone in 1917 firmly believed, was static and eternal, neither growing nor shrinking. The galaxies were not visibly falling together. Something had to be holding the universe up against its own gravity. So Einstein did something he would later bitterly regret. He added a new term to his equations by hand. A term that represented a kind of built-in repulsion spread evenly throughout all of space, an outward pressure of the vacuum itself that would exactly balance the inward pull of all the matter. He called this term the cosmological constant. With it carefully tuned, his equations could describe a static universe, perfectly poised between collapse and expansion, the inward pull of matter balanced against the outward push of empty space. It was an elegant fix for a problem that, as it turned out, did not actually exist. Because the universe was not static at all. The truth arrived from a mountaintop in California. At the Mount Wilson Observatory, perched above the city of Los Angeles, the astronomer Edwin Hubble spent the 1920s studying faint smudges of light that had long been mysteries. He proved that these smudges were not clouds within our own galaxy, but entire separate galaxies, islands of billions of stars, lying at almost unimaginable distances. And then he measured something even more profound. By analyzing the light from these distant galaxies, Hubble found that almost all of them were moving away from us, and that the farther away a galaxy was, the faster it was receding. This was the discovery, announced in the year 1929, that the universe is not static, the universe is expanding. Space itself is stretching, carrying the galaxies apart from one another like raisins in a rising loaf of bread. When Einstein learned of Hubble's discovery, he realized at once that he had made a terrible mistake. If only he had trusted his own equations, with their refusal to permit a static universe, he could have predicted the expansion years before Hubble ever observed it. Instead, he had bolted on an unnecessary correction to force the universe into a shape it did not have. He removed the cosmological constant from his equations, and according to a story told by the physicist George Gamow, called it the biggest blunder of his life. The repulsive term was discarded, dismissed as the embarrassing relic of an error. For most of the 20th century, the cosmological constant sat in the textbooks as a historical footnote, a famous mistake by a famous genius. And then, at the very end of the century, it came roaring back from the dead, and it brought with it the most disturbing discovery in modern cosmology. The story of its return centers on a particular kind of exploding star. When certain dense dead stars accumulate too much matter, they detonate in a colossal explosion called a Type I supernova. These explosions are extraordinarily useful to astronomers because they all blaze with very nearly the same intrinsic brightness. They are, in effect, standard candles. If you know how bright a candle truly is, and you measure how dim it appears from a distance, you can calculate exactly how far away it is. By hunting for these exploding stars in extremely distant galaxies, astronomers could measure cosmic distances with unprecedented precision, and by comparing those distances with the speeds at which the galaxies were receding, they could trace out the history of the universe's expansion across billions of years. In the 1990s, two rival teams of astronomers set out to do exactly this. One was the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory in California. The other was the High Z Supernova Search Team, led by Brian Schmidt and including a young astronomer named Adam Rees. Both teams were trying to answer what seemed like a straightforward question. The universe was expanding, everyone knew that, but gravity should be slowing that expansion down, since all the matter in the universe is pulling on all the rest of it, gently applying the brakes to the cosmic flight. The two teams expected to measure exactly how much the expansion was decelerating, and from that to learn the eventual fate of the universe, whether it would expand forever or one day collapse back together. What they found, when the data finally came in around the year 1998, astonished and frightened everyone involved, including themselves. The distant supernovae were fainter than they should have been. They were farther away than a steadily decelerating universe could explain. The expansion of the universe was not slowing down. It was speeding up. Some unknown influence was pushing the galaxies apart faster and faster, overpowering the collective inward pull of all the matter in the cosmos. Both teams, working independently and in competition, arrived at the same impossible conclusion, and they checked it and rechecked it, because no one wanted to be the one to announce something so strange and be proven wrong. But the result held. The universe was accelerating, and the only thing in Einstein's equations that could drive such an acceleration was the very term he had discarded as his greatest blunder. The cosmological constant was real after all. Empty space really does push. This mysterious repulsive influence was given a name. It is called dark energy, and it is, by a wide margin, the most abundant thing in the universe. When astronomers add up everything the cosmos contains, the ordinary matter that makes up stars and planets and people accounts for only a small slice, less than 5% of the total. The mysterious dark matter that we will not fully explore here makes up a larger portion, perhaps 27%. But the great remainder, roughly 68% of everything that exists, the dominant ingredient of the entire universe, is this dark energy, this strange repulsive tension woven invisibly through all of empty space. Most of reality, it turns out, is made of the one thing that pushes. So we can finally return to the question that began this entire journey and give it a far more honest and far more unsettling answer. Does gravity only pull? On the scale of your body, the answer is yes, always. On the scale of the Earth and the Moon, yes. On the scale of the Sun and its planets, yes. On the scale of our galaxy, and even of the clusters of galaxies bound tightly together by their mutual attraction, yes, gravity pulls and only pulls. But zoom out far enough, to the very largest scales of the cosmos, to the vast and nearly empty gulfs between the great clusters of galaxies, and the picture inverts completely. Out there, in the emptiness, dark energy dominates, and its gravity is repulsive. Out there, the universe is being pushed apart, and the push is growing stronger with every passing moment. The simple childhood truth that gravity only pulls is correct in your kitchen and a lie across the cosmos. The largest gravitational fact about the universe is not attraction, it is repulsion. And this repulsion has a quality that makes it far more disturbing than any ordinary pushing force. Dark energy does not weaken as the universe expands. This is the part that is genuinely hard to absorb. Ordinary matter thins out as space stretches, its gravity weakening as the galaxies spread apart. But dark energy appears to be a property of empty space itself, and so as more space comes into being, there is simply more dark energy along with it. The expansion creates new space, and the new space carries new dark energy, which drives the expansion faster, which creates yet more space, in a relentless cycle that builds upon itself without end. The push does not fade, the push accelerates. The universe is not merely flying apart, it is flying apart faster and faster, with no force in nature strong enough to ever bring it back. Consider what this means for the distant future of the night sky. Right now, on a clear dark night, far from the lights of any city, you can look up and see the faint band of our own galaxy, and with a telescope you can glimpse other galaxies far beyond it, scattered across the deep. But as the expansion accelerates, the most distant galaxies are receding from us faster and faster, and eventually they will recede so quickly that their light can no longer reach us at all. One by one, over billions of years, the galaxies will slip beyond the horizon of the visible universe, their light stretched and dimmed, and finally extinguished from our sky. The cosmos is slowly emptying itself before our eyes, too slowly for any human to witness, but relentlessly all the same. In the far distant future, astronomers on whatever worlds may then exist will look up into a sky that holds only their own galaxy, surrounded by an absolute and featureless darkness, with no hint anywhere that other galaxies ever existed at all. They will have no way of knowing about the grand expanding cosmos we can still see today. The evidence will have been pushed beyond their reach forever, carried away on the swelling tide of repulsive gravity. There is a strange and lonely melancholy in this. We live, it turns out, in a privileged and fleeting moment in the history of the universe, a moment when the sky is still full, when the other galaxies are still close enough to see, when the great structure of the cosmos still lies open to our instruments and our wonder. We arrived in time to witness it. The beings who come long after us will not. The pushing force, the one form of gravity we were told could not exist, is quietly carrying the universe away into the dark, and there is nothing anyone can ever do to stop it. The force we trusted to only pull is, in its largest and most powerful form, a force of separation, of distance, of an ever-deepening loneliness spread across all of space. And it is winning. We have now seen gravity wear two opposite faces. We have seen it pull, as ordinary matter always does, drawing the apple to the ground, and the moon to the earth, and the earth to the sun. And we have seen it push, as dark energy does, driving the entire universe apart faster and faster across the emptiest reaches of space. So the simple question has split into a deeper and more demanding one. Why does ordinary matter always pull? Not just because mass comes in one sign, though that is true. We want to know what lies beneath that fact. We want to know what it is about the deepest machinery of nature that forces ordinary matter to attract. And we want to understand why the universe seems to have begun with a violent burst of the pushing kind of gravity before settling into the pulling kind. To answer this, we have to go all the way down to the smallest scales and the earliest moments, and then all the way back up again. Let us begin at the very beginning, in the first unimaginably tiny fraction of a second after the universe came into being. For most of the 20th century, cosmologists pictured the early universe simply expanding outward from an intensely hot and dense beginning, slowing gradually as gravity applied its brakes. But this simple picture had deep problems that no one could explain. The universe looked far too uniform. Regions on opposite sides of the sky, so far apart that light could never have travelled between them, somehow had almost exactly the same temperature, as if they had agreed on it in advance, which should have been impossible. And the overall geometry of the universe was balanced on an impossibly fine knife edge, neither curving in on itself nor flying apart in shape, but flat to a precision that seemed to demand an explanation. These puzzles sat unsolved for decades, quietly nagging at anyone who thought hard about the early cosmos. The solution came to a young physicist named Alan Guth in the late 1970s and the very first days of the 1980s. Guth was working late one night, the story goes, wrestling with these problems, when he realized that they could all be solved at a single stroke if the infant universe had undergone a brief but staggering burst of accelerating expansion in its very first moments. He called this idea inflation. For the tiniest sliver of a second after the beginning, far less than a trillionth of a second, the universe is thought to have expanded not gradually but explosively, doubling in size again and again and again, growing by an almost incomprehensible factor in almost no time at all. A region smaller than a single atom was blown up to a size larger than a grapefruit, and then far larger still, in the blink of a moment so brief that no human word for time can do it justice. And what drove this explosive expansion? The same thing that drives the gentler acceleration we see today. A field filling all of space with a strong negative pressure, and therefore with repulsive gravity. Inflation is, at its heart, the early universe falling under the spell of an enormously powerful version of the pushing kind of gravity. Before there were atoms, before there were stars, before there was anything at all that we would recognize, the universe was ruled not by attraction, but by repulsion, by a gravity that pushed with such violence that it laid down the smooth, flat, uniform canvas on which everything else would later be painted. The pulling kind of gravity, the kind that would eventually build the galaxies, did not come first. It came afterward, once inflation ended and the repulsive field decayed into a sea of ordinary hot matter and energy. The universe begins with a push, and only later learns to pull. The order matters. The push made the smoothness, and the pull, working patiently on the tiny ripples left behind, made everything else. This is one of the most beautiful and humbling ideas in all of science, and it is worth holding for a moment before we move on. The structure you see around you, the stars and galaxies and the warm world beneath you, all of it grew from microscopic quantum ripples present during inflation, ripples stretched to enormous size by that first explosive expansion, and then slowly, over billions of years, gathered together by attractive gravity into the great cosmic web. The pushing gravity stretched the seeds, the pulling gravity grew the harvest. Both faces of gravity, the push and the pull, were necessary to make a universe with anyone in it to wonder about gravity at all. But none of this yet tells us the deepest reason ordinary matter attracts. For that, we have to leave the grand scale of cosmology entirely and shrink down to the realm of the very smallest things, to the strange and probabilistic world of quantum physics. Because in that world, forces are not mysterious influences reaching invisibly across space. In that world, every force is carried by particles. When two electrically charged particles push or pull on one another, they do so in the quantum picture by exchanging tiny particles of light called photons, flung back and forth between them like a ball tossed between two players. The strong nuclear force that binds the atomic nucleus together is carried by particles called gluons. The weak nuclear force, responsible for certain kinds of radioactive decay, is carried by heavier particles. Every force has its carrier, its messenger particle that conveys the influence from one object to another. And gravity, in this quantum picture, should have a carrier too. Physicists have given it a name, even though it has never been directly detected and may never be. They call it the graviton. It is the hypothetical particle that would carry the gravitational force, flung between masses the way photons are flung between charges. We must be honest here. The graviton remains entirely theoretical. No experiment has ever caught one, and detecting a single graviton may be forever beyond our reach, because gravity is so unimaginably weak. But the mathematics of how such a particle would have to behave is well understood, and within that mathematics lies the deepest answer to our entire question. Here is the remarkable thing. The behavior of a force, whether it pulls like charges together or pushes them apart, is determined by a single property of its carrier particle, a property called spin. Spin is a quantum characteristic, a kind of intrinsic rotation that every fundamental particle possesses, and it comes in whole numbers and half numbers. And there is a deep and beautiful rule, proven in the mathematics of quantum field theory, that connects the spin of a force carrier to the very nature of the force it carries. The rule is this: if the carrier has an odd amount of spin, then like charges repel one another, and opposite charges attract. If the carrier has an even amount of spin, then everything attracts everything, with no repulsion at all. The photon, the carrier of electromagnetism, has a spin of exactly 1. 1 is an odd number, and so electromagnetism behaves exactly as the rule predicts. Like charges, two positives or two negatives repel each other, while opposite charges attract. This is why electricity both pushes and pulls. It is a direct consequence of the photon having a spin of 1. Now consider the graviton. The graviton, if it exists, must have a spin of exactly 2, and physicists know this because of the precise mathematical way that gravity couples to energy and pressure, a way that demands a spin of 2 and permits no other value. 2 is an even number, and so gravity must follow the even spin rule. Everything attracts everything. There can be no repulsion between like sources, because for gravity there is only one kind of source to begin with, and all of it attracts all of the rest. This is the deepest answer that physics can currently give to the question of why gravity only pulls. It pulls because its carrier has a spin of 2, and a spin 2 force, by the unbreakable logic of quantum mathematics, can only attract. Sit with how strange and wonderful that is. The reason you are held gently to your bed tonight, the reason the apple fell in Newton's garden, the reason the galaxies gathered out of the primordial dark, traces all the way down to a single even number, the spin of a particle that no one has ever seen, and perhaps no one ever will. The whole vast architecture of cosmic attraction rests upon the difference between odd and even. Electromagnetism, built on the odd number 1, both pushes and pulls. Gravity, built on the even number 2, can only pull. The universe attracts because of the difference between an odd number and an even one. And that difference, woven into the deepest mathematics of reality, shapes everything that has ever fallen, everything that has ever orbited, everything that has ever been drawn together across the dark. Still, a doubt might linger. We have said there is no negative mass, no opposite gravitational charge to create repulsion the way negative electric charge creates it. But how certain can we really be? Surely somewhere in the universe, in some exotic form of matter, there might be something that gravity pushes rather than pulls. The most natural place to look for such a thing is in antimatter. For every kind of particle in the universe, there exists a mirror image antiparticle, identical in mass but opposite in electric charge. The electron has its antiparticle, the positron, carrying positive charge instead of negative. When a particle meets its antiparticle, the two annihilate in a flash of pure energy. For decades, a tantalizing question hung in the air, unanswered because it was so fiendishly difficult to test. Does antimatter fall down, like ordinary matter, or does it fall up? Could antimatter be the long-sought substance that gravity repels? The trouble was that antimatter is extraordinarily hard to make, and even harder to keep, since it annihilates the instant it touches ordinary matter. To test how it falls, physicists needed to create atoms of antimatter, trap them in a vacuum without ever letting them touch the walls of their container, hold them perfectly still, and then watch which way they drifted when released. This is one of the most delicate experiments ever conceived, and it was finally carried out at the Great Particle Physics Laboratory called CERN, near the city of Geneva on the border between Switzerland and France. In an experiment named Alpha, researchers managed to create atoms of antihydrogen, the antimatter version of the simplest atom, and to hold them suspended in a magnetic trap. Then, in results announced in the year 2023, they carefully switched off the trap and watched which way the antimatter atoms fell. The answer, after all the difficulty and all the waiting, was clear and unambiguous. Antimatter falls down. It falls the same way ordinary matter does, pulled toward the Earth by the same attractive gravity, at the same rate. There is no anti-gravity hidden in antimatter. The mirror world of antimatter is pulled downward just as firmly as our own. So the escape hatch closes. Even antimatter, the most exotic ordinary substance we can create, obeys the one-way pull. Imagine a perfect mirror image of yourself, built entirely of antimatter, an antimatter twin in some impossible parallel laboratory. That twin would not float upward away from the floor. That twin would stand on the ground exactly as you do, held down by gravity exactly as you are. The universe extends no special privilege to antimatter. It pulls everything, matter and antimatter alike, toward everything else, with the same patient and inescapable insistence. Is there then nothing at all in the universe that gravity pushes, apart from the strange dark energy filling empty space? The honest answer is that there is one more candidate, but it is faint, fragile, and almost entirely theoretical. To make gravity repel locally, you would need genuine negative energy, a region where the energy is actually less than the energy of empty space itself, a kind of hole dug below the floor of nothingness. And remarkably, quantum physics permits tiny fleeting amounts of exactly this. The phenomenon is called the Casimir effect, named after the Dutch physicist Hendrik Casimir, who predicted it in the year 1948 while working at a research laboratory in the Netherlands. Casimir realized that if you placed two flat metal plates extremely close together in a vacuum, the empty space between them contains slightly less energy than ordinary empty space, because the close plates exclude certain fluctuations of the quantum fields that fill the vacuum everywhere. The result is a region of genuinely negative energy density and a tiny measurable force pulling the plates together. This effect is real and has been measured in laboratories, but the amount of negative energy it produces is vanishingly small, far too little to create any noticeable repulsive gravity, and confined to the microscopic gap between two plates pressed almost into contact. This tiny effect has fueled some of the most speculative dreams in all of physics. Dreams of warp drives and wormholes, of bending space-time to travel faster than light, or to open shortcuts between distant places. In the year 1994, the physicist Miguel Alcubierre showed that Einstein's equations technically permit a kind of warp bubble, a region of contracted space ahead of a ship and expanded space behind it, that could in principle carry a traveller across the cosmos faster than light without ever locally exceeding the speed of light. But the catch, the enormous and perhaps fatal catch, is that building such a bubble would require vast quantities of negative energy, far more than the feeble whisper the Casimir effect provides. Perhaps more negative energy than exists in any form we know how to create. These remain, for now, mathematical curiosities, permitted by the equations but utterly beyond our reach, tantalizing hints that the universe might in principle allow the pushing of spacetime, while offering us no practical way to ever do it. The honest truth is that nobody knows whether such things are truly possible, and the gap between what the equations permit and what nature actually allows may be unbridgeable. So we are left with a universe whose deepest rule, at the scale of stars and planets and bodies, is attraction without exception. Gravity pulls because its carrier has even spin. There is no negative mass to oppose it. Antimatter falls down just like everything else. And the only known exceptions, the dark energy of empty space and the faint negative energy of the Casimir effect, are either too vast and diffuse to feel in any ordinary place, or too tiny and fragile to matter at all. In your room, in your world, in your galaxy, the rule holds absolutely. Everything pulls everything. There is no shelter, no shield, no exception, no escape. And it is precisely this absoluteness, this refusal of gravity to ever push back against itself, that leads to the most extreme and terrifying objects the universe contains. Because a force that can only pull, given enough matter in one place, has no way to ever stop pulling. And when nothing can stop the pulling, the result is collapse without limit, a falling that never ends, the formation of the darkest and most absolute objects in all of creation. There is a consequence of one-way gravity so profound and so unsettling that it deserves the longest and most careful look of all. Think for a moment about what it means for a force to only ever pull, with no possibility of pushing back against itself. Every other force in nature has a built-in limit, a point at which it begins to resist further compression. Squeeze ordinary matter hard enough, and the electric forces between its atoms push back, harder and harder, refusing to let the atoms overlap. Squeeze the atomic nuclei themselves, and the nuclear forces resist. In every ordinary situation, there is a pushing force waiting in reserve, ready to halt the squeezing once it goes too far. This is why a chair holds you up, why the ground does not swallow you, why a rock stays a rock and does not crush itself into nothing. Pushing forces set limits. They draw lines that cannot be crossed. Gravity sets no such limit, because gravity cannot push. And there is something even worse hidden in Einstein's equations, something we touched on earlier and must now confront fully. Recall that pressure gravitates. In ordinary matter, pressure is the great resistance to collapse, the outward push that holds things up against gravity's pull. But pressure, being a source of gravity in its own right, also adds to the very pull it is trying to resist. For ordinary objects, this is a negligible whisper, but in an object massive enough and compressed enough, the pressure required to hold it up becomes so enormous that its own gravitational contribution starts to matter. And here the trap snaps shut. The harder the matter pushes back, the stronger its gravity becomes, and the stronger its gravity becomes, the harder it must push back, in a vicious spiral that ordinary forces cannot escape. Beyond a certain point, every attempt to resist collapse only deepens the collapse. The very pressure meant to save the object becomes part of what destroys it. No other force in the universe behaves this way. Only gravity, the force that cannot push, can turn an object's own resistance into the instrument of its doom. To see how this plays out, consider the life of a star. A star is, at its heart, a long and delicate war between two opposing tendencies. Gravity is forever trying to crush the star inward, to collapse all that mass toward the center. Pushing back against this crush is the immense outward pressure generated by nuclear fusion in the star's core, where hydrogen is fused into helium, releasing the energy that makes the star shine. For billions of years, these two forces hold a near-perfect balance, gravity pulling in and fusion pushing out, the star steady and luminous and alive. But fusion requires fuel, and no supply of fuel is infinite. Eventually, every star exhausts the material in its core, the fusion falters, and the outward pressure that held gravity at bay begins to fail. And when the pressure fails, gravity, patient and relentless, finally has its way. The star begins to collapse. What happens next depends entirely on how much mass the star contains, and the story of how this was first understood is one of the most poignant in the history of science. In the year 1930, a brilliant young Indian physicist named Subrahmanyan Chandrasekhar boarded a ship bound from India to England, where he was to begin his studies at Cambridge. He was just 19 years old. To pass the long weeks of the ocean voyage, he worked through the mathematics of dying stars, and on that ship, somewhere on the open sea, he discovered something extraordinary. He calculated that there is a maximum mass beyond which a dying star cannot support itself against gravity by the ordinary means available to it. Below a certain mass, roughly 1 4/10 times the mass of our Sun, a collapsing star can stabilize as a white dwarf, an Earth-sized ember held up by a strange quantum pressure of its packed electrons, refusing to be squeezed any further. But above that critical mass, even this quantum pressure fails, and there is nothing left to stop the fall. The young man had found a limit written into the fate of the stars, a threshold beyond which gravity simply wins. When Chandrasekhar presented his result, the most eminent astrophysicist of the age, Arthur Eddington, the very man who had confirmed Einstein's bending of starlight, publicly ridiculed the idea. Eddington could not accept that nature would permit a star to collapse without limit, and he dismissed the young Chandrasekhar's mathematics in front of a gathered audience, a humiliation that wounded the younger man deeply and delayed the acceptance of his work for years. But Chandrasekhar was right, and Eddington was wrong, and in time the world came to understand it. Decades later, Chandrasekhar would receive the highest honours his field could offer for the work he had done as a teenager on that ship. Nature does permit a star to collapse without limit. The limit he had found was real, and crossing it leads somewhere very strange indeed. For stars somewhat above Chandrasekhar's limit, the collapse halts at a more extreme stage, forming a neutron star, an object so dense that the electrons and protons of its matter have been crushed together into neutrons, packed as tightly as the particles in an atomic nucleus. A neutron star squeezes more mass than our entire Sun into a sphere only a dozen miles across, so dense that a single thimbleful of its material would weigh as much as a mountain. For a while, a new quantum pressure, this time from the packed neutrons themselves, holds the collapse at bay. But there is yet another limit, a second threshold, somewhere between 2 and 3 times the mass of the Sun, beyond which even the pressure of packed neutrons fails. And once that final threshold is crossed, there is nothing left. No known force, no quantum pressure, no resistance of any kind can stop the collapse. The matter falls inward, and it keeps falling, and nothing in the universe can ever halt it again. The result is the strangest object that physics describes. The result is a black hole. The mathematics of the black hole was worked out with breathtaking speed and under the most extraordinary circumstances. Only months after Einstein published his theory of general relativity in late 1915, a German physicist named Karl Schwarzschild found an exact solution to Einstein's notoriously difficult equations. A solution describing the spacetime around a perfectly spherical mass. And Schwarzschild did this while serving as an artillery officer on the Russian front during the First World War, working out the deepest geometry of the cosmos amid the mud and cold and danger of the trenches. He sent his solution to Einstein, who was astonished that anyone had found an exact answer so quickly. Tragically, Schwarzschild contracted a rare and painful illness at the front, and died only months later, never living to see how profoundly important his solution would become. But his work revealed something Einstein himself found difficult to believe. The equation said that if you compressed enough mass into a small enough sphere, you would create a region of space from which nothing, not even light, could ever escape. The boundary of that region is called the event horizon, and it marks the most absolute frontier in all of nature. To understand it, recall the idea of escape velocity. the speed you would need to fling an object away from a planet fast enough that gravity could never pull it back. On Earth, the escape velocity is around 25,000 miles per hour. The more massive and compact an object is, the higher its escape velocity climbs. Now imagine compressing matter until the escape velocity reaches the speed of light itself, the ultimate speed limit of the universe, beyond which nothing can travel. At that point, not even light, the fastest thing there is, can move quickly enough to escape. And once light cannot escape, nothing can, because nothing outruns light. This is the event horizon, the surface at which escape becomes impossible, the point of no return. Cross it, and you can never come back, never send a signal back, never so much as glimpse the outside universe again. The event horizon is not a physical surface, not a wall you would strike. It is simply a line drawn in empty space, marking the threshold beyond which all paths lead inward, and none lead out. There is a way of picturing this that captures the horror of it more vividly than any equation. Imagine space itself as a flowing river, pouring inward toward the black hole, faster and faster as it approaches. Far away, the river flows slowly, and you can easily swim against it back to safety. Closer in, the current quickens, and you must swim harder. At the event horizon, the river of space is flowing inward at exactly the speed of light. To swim against it, to escape, you would have to swim faster than light, which nothing can do. And inside the horizon, the river flows inward faster than light itself, sweeping everything helplessly toward the center, no matter how powerfully it tries to flee. You are not pulled into a black hole the way you are pulled toward the Earth. You are carried in, on a current of falling space, toward a destination from which there is no return, and about which our deepest theories fall silent. What would it be like to fall toward such a thing? If you fell toward a black hole formed from a single collapsed star, you would die long before reaching the horizon, and you would die in a manner so grotesque that physicists have given it a darkly whimsical name. Because gravity grows so rapidly stronger as you approach, the pull on your feet, if you fell feet first, would be enormously greater than the pull on your head, since your feet would be closer to the center. The difference would stretch you, pulling your body lengthwise like soft dough, while at the same time squeezing you from the sides, until you are drawn out into a long, thin thread of matter. Physicists call this spaghettification, the stretching of an object into a strand of spaghetti by the savage gradient of gravity near a small black hole. You would be torn apart not by being crushed all at once, but by the difference in gravity's pull across the length of your own body. The relentless stretching of a force that only pulls, pulling harder on the near side than the far side, until nothing held together at all. And here the warping of time, which we met earlier in the gentle towers of Harvard, returns in its most extreme and dreamlike form. Near a black hole, time slows so dramatically that the experience of falling in becomes almost impossible to describe. If you watched a friend fall toward a black hole from a safe distance, you would never actually see them cross the horizon. Instead, as they approached it, their fall would appear to slow and slow, their image growing dimmer and redder, the light from them stretched out by the warping of time, until they seemed to freeze forever just outside the horizon, hovering motionless and fading, an afterimage burned into the edge of the dark. From your distant vantage, they would take an infinite time to cross, but from their own point of view, falling inward, nothing strange would happen at the horizon at all. They would cross it in an ordinary moment, perhaps without even noticing, and continue inexorably toward the center. Two observers, two utterly different stories, both completely true, separated by the warping of time around a force that will not stop pulling. This is the strange gift and curse of relativity. There is no single answer to when the fall ends. The answer depends entirely on who is watching. At the very center of a black hole, the equations predict something they cannot actually describe, a point where the matter has collapsed to infinite density and the curvature of spacetime becomes infinite, a place called the singularity. But the honest truth is that no one knows what is really there, because at the singularity our theories break down completely and stop giving sensible answers. General relativity, which has triumphed in every other test, simply fails at the center of a black hole, predicting infinities that surely cannot be physically real. To understand what truly lies at the heart of a black hole, we would need a theory that unites gravity with quantum physics. A theory that does not yet exist despite a century of the greatest minds searching for it. The center of a black hole is, quite literally, a place where our knowledge ends. It is one of the few honest blank spaces left on the map of physics. A region where the only truthful thing a scientist can say is that nobody knows. For most of the 20th century, black holes remained purely theoretical, objects permitted by the equations but never actually seen. And many physicists, including at times Einstein himself, doubted they could really exist. But over the past few decades, the evidence has become overwhelming and then, finally, direct. The most spectacular confirmation came from one of the most ambitious experiments ever built, a pair of enormous instruments designed to detect gravitational waves, the ripples in spacetime that Einstein had predicted back in the year 1916. When two black holes spiral together and merge, they shake the fabric of spacetime so violently that ripples spread outward across the universe at the speed of light, stretching and squeezing everything they pass through by an almost infinitesimally small amount. The instruments built to catch these ripples, located in the United States and known together as the Gravitational Wave Observatory, use laser beams traveling down tunnels miles long to measure changes in distance smaller than a fraction of the width of a single proton. On the 14th of September in the year 2015, these instruments detected their first signal. It had come from two black holes, each roughly 30 times the mass of our Sun, that had spiraled together and merged in a catastrophic collision more than 1 billion light-years away. The light from that event, had it been light, would have left its source over 1 billion years ago, before complex life had even arisen on Earth, and travelled across the dark all that time to arrive at the exact moment our instruments switched on. In the final fraction of a second of the merger, an amount of mass equal to roughly 3 entire suns was converted into the pure energy of gravitational waves, briefly outshining, in this invisible form of radiation, all the stars in all the galaxies of the visible universe combined. Space-time itself rang like a struck bell, and we heard it. The discovery confirmed at a single stroke that gravitational waves are real, that black holes are real, and that they merge exactly as the equations predict. The scientists who led the effort, Rainer Weiss, Kip Thorne, and Barry Barish, received the highest honor in physics for the achievement. A prediction made on paper a century earlier had finally been caught. A tremor in the fabric of reality from the collision of two of the darkest objects the universe contains. And then, only a few years later, we saw one directly. Using a network of radio telescopes spread across the entire Earth, working together as a single instrument as wide as the planet, astronomers captured an actual image of the region around a black hole. In the year 2019, they revealed a picture of the supermassive black hole at the heart of a distant giant Galilee called Messier 87, a monster billions of times the mass of our Sun, shown as a dark circle of nothingness, ringed by a glowing halo of hot matter spiraling toward its doom. A few years after that, the same network turned its gaze toward the center of our own galaxy and imaged the great black hole that lurks there, at the very heart of the Milky Way, around which our entire galaxy slowly turns. The dark shadow at the center of these images is the event horizon itself, the boundary of no return, captured in light for human eyes to see. We have now not only felt the ripples of black holes colliding, we have looked upon their darkness directly and seen the shape of the place where gravity, the force that only pulls, has pulled so hard that it tore a hole in the visible universe. It is worth pausing to absorb the deepest lesson of all this. Black holes exist because gravity cannot push. Every other process of collapse in the universe eventually halts, stopped by some pushing force that resists further compression. Only gravity has no such stop, no reserve of repulsion to call upon, and so only gravity can collapse an object all the way down, past every barrier, into a singularity where knowledge itself runs out. The black hole is the ultimate expression of one-way gravity, the purest demonstration of what it means for a force to only ever pull and never push. It is attraction taken to its absolute logical conclusion, a pulling so total that not even light can answer, and the same logic that governs the death of stars governs the fate of the entire universe, though it pulls in two opposite directions at once. On the small scale, gravity pulls relentlessly, gathering matter together, building stars and planets and galaxies, and occasionally collapsing the largest of them into black holes from which nothing returns. On the largest scale, the repulsive gravity of dark energy pushes relentlessly, driving the galaxies apart, stretching the cosmos thinner and emptier with every passing eon. The far future of the universe is a contest between these two faces of gravity, and as best we can tell, the pushing is destined to win the war, while the pulling wins every local battle. The galaxies bound together by attraction will hold, but they will drift ever farther from one another across an expanding void, until each isolated island of stars sits alone in an ocean of darkness, cut off forever from all the rest. Within each island, the stars will one by one burn out and die, the gas to make new stars will run dry, and the long cold darkness will deepen across trillions upon trillions of years. Some physicists wonder whether the repulsive force might even strengthen over time, until one day it grows powerful enough to tear apart not just the spaces between galaxies, but the galaxies themselves, then the stars, then the planets, and finally the very atoms, in a final catastrophe sometimes called the Great Tearing. The universe ripping itself to shreds at the hands of a gravity that pushes. Whether that grim ending comes to pass, or whether instead the universe simply fades into a cold and endless quiet, the honest answer is that nobody yet knows. But hold this thought, and let it settle gently over everything we have learned. The same force is at work in all of it. The tender pull that holds you to your bed tonight, the pull that lets a child stand upright and a river run downhill, and a leaf settle softly to the ground, is the very same force, differing only in degree, that crushes a dying star past the point of no return, and tears a hole in the visible universe. There is no separate gentle gravity and savage gravity. There is only gravity, the one-way pull, expressed faintly in the warmth of an ordinary world and monstrously in the dark of a collapsed star. The hand that holds you and the hand that destroys a star are the same hand. It is only a question of how much, and the question of how much does not end with a single dying star. It extends outward, across the entire universe, and forward, across spans of time so vast that the mind has no machinery built to hold them. We have followed the one-way pull from the warmth of an ordinary bed to the crushing dark of a collapsed star. Now we must follow it to the end of time itself. Because gravity does not stop when a star dies, and the universe does not end when the last sun goes out. Consider what a black hole truly is, once it has formed. For most of the 20th century, physicists believed that a black hole was the most permanent object that could possibly exist. Nothing escapes it. Nothing returns from it. Matter falls in and is gone forever, and the hole simply waits, eternal and unchanging, until the end of everything. A black hole seemed to be the one truly immortal thing in a universe where everything else decays. That belief was wrong. Not slightly wrong. Profoundly, beautifully wrong. In 1974, a young physicist at the University of Cambridge named Stephen Hawking proved something that nobody had expected, and almost nobody had wanted to be true. He showed that black holes are not perfectly black. They glow. Very faintly, almost imperceptibly, a black hole radiates energy into the space around it. And because it radiates energy, it slowly loses mass. And because it loses mass, it eventually, given enough time, disappears entirely. The most permanent object in the universe turned out to be temporary after all. The reason is one of the strangest ideas in all of physics, and it emerges from the place where gravity meets the quantum world. Empty space, according to quantum mechanics, is not truly empty. At the smallest scales, The vacuum seethes with pairs of particles that flicker into existence and then annihilate one another almost instantly, borrowing energy from nothing and paying it back before the universe can notice. This is not speculation. The effects of these flickering pairs have been measured in laboratories. They are part of the deep structure of reality, and near the edge of a black hole, at the event horizon, something happens to these pairs that turns the vacuum into a slow and patient thief. When a pair of these particles appears right at the edge of the horizon, it can happen that one of them falls inward, across the boundary, lost forever, while the other escapes outward into space. The escaping particle carries away a tiny sliver of energy, and that energy, by the strict accounting of the universe, must be subtracted from the mass of the black hole itself. The hole has in effect radiated a particle. It has grown infinitesimally lighter. Repeat this process across the entire surface of the horizon, continuously, for an unimaginable length of time, and the black hole slowly evaporates, like a puddle drying in a desert that has no sun. The rate is almost beyond belief in its slowness. A black hole with the mass of our sun would radiate so faintly that it would take roughly 10 to the 67th power years to evaporate completely. To write that number, you would put a 1 and then follow it with 67 zeros. The current age of the entire universe from the beginning until tonight is less than 14 billion years. That is a number with merely 10 digits. The lifetime of a single solar mass black hole is a number so much larger that the age of the cosmos so far is not even a rounding error within it. It is closer to nothing. And the largest black holes last far longer still. At the center of our galaxy sits a black hole roughly 4 million times the mass of the Sun. At the centers of the largest galaxies sit black holes billions of times heavier. A truly enormous black hole might take 10 to the 100th power years to evaporate. That number has a name. It is called a googol, a 1 followed by 100 zeros. There is not enough matter in the observable universe to write that number out in atoms. 1 atom per zero, if you wrote it across the entire visible cosmos. And yet that is roughly how long the final largest black holes will linger before they too release their last faint shudder of radiation and wink out of existence. This gives us, for the first time, a way to think about the future of everything, not in years, which become meaningless, but in eras. In 1997, two astrophysicists, Fred Adams and Gregory Laughlin, laid out a framework for the entire future history of the universe, dividing the almost endless span ahead into a sequence of great ages, each one dimmer and emptier than the last. We are living, right now, in the first and brightest of these ages, and it is worth understanding what comes after it, because the same one-way pull that holds you in your bed tonight is the architect of every age to come. We live in what they called the stelliferous era, the age of stars. It is the chapter of cosmic history in which the sky is full of light, in which galaxies blaze with hundreds of billions of suns, in which new stars are still being born from clouds of gas and dust. It feels permanent to us, because it is all we have ever known and all our ancestors ever knew. But it is a passing phase. The universe is converting its gas into stars and burning those stars, and it cannot do this forever. The fuel is finite. The lights are, very slowly, going out. Star formation across the universe has already passed its peak. The great age of star birth happened billions of years ago, when the cosmos was young and dense with gas. Today, galaxies form new stars at a fraction of the rate they once did. And as the gas is used up, locked away inside dead stellar remnants, or scattered too thinly to ever collapse again, the rate of new births will keep falling. In roughly 100 trillion years, the last new star will form from the last available wisp of gas. After that, no more suns will ever ignite. The cosmos will be lit only by the stars that already exist, slowly burning down toward darkness. The longest-lived stars will be the smallest ones. This is one of the gentle ironies written into the physics of gravity and fusion. The great brilliant blue stars, the ones that blaze with the light of 100,000 suns, burn through their fuel in only a few million years, and die young in catastrophic explosions. But the smallest stars, the dim red dwarfs that are too faint to see with the naked eye even when they are close, sip their fuel so slowly that they can burn steadily for trillions of years. The smallest red dwarfs may glow for 10 trillion years or longer, far outlasting every brilliant giant. When the universe is 1,000 times older than it is now, these dim red embers will be the last stars still shining, and then, one by one, even they will fade. What follows is the degenerate era, the age of the remnants. By this point, every star has died, and what remains are the cold corpses they left behind. White dwarfs, the dense glowing cinders of stars like our Sun, slowly cooling toward the temperature of the surrounding void. Neutron stars, the impossibly compressed cores left by larger stars. Brown dwarfs, the failed stars that never had enough mass to ignite at all. And black holes, scattered through space where the most massive stars once lived and died. There is no starlight in this era. There is only the faint, fading warmth of objects that were once stars, radiating away the last of their heat into a darkness that grows colder with every passing eon. And even the galaxies themselves do not survive this age intact. Over spans of time vast beyond comprehension, the gravitational dance of stars within a galaxy slowly comes apart. Through countless near misses and gravitational encounters, some stellar remnants are flung outward, escaping into the empty space between galaxies, while others lose energy and spiral slowly inward, falling at last into the supermassive black hole at the galactic center. The galaxy that took billions of years to assemble itself, drawn together by the patient one-way pull, is slowly disassembled by that same pull, scattered and swallowed until nothing recognizable remains. Here we reach one of the deepest and most uncertain questions in all of physics, and honesty requires that we treat it as the open question it truly is. The question is whether matter itself is stable, whether the protons that sit at the heart of every atom in your body, in this room, in every cold dead remnant drifting through the future dark, will last forever. Some of our best theories, the grand attempts to unify the forces of nature, predict that the proton is not perfectly stable, that given enough time, a proton will spontaneously decay, dissolving into lighter particles and radiation, the atom it anchored quietly ceasing to be. This has never been observed. Deep beneath a mountain in Japan, in an enormous tank holding 50,000 tons of ultra-pure water, an experiment called Super Kamiokande has watched for years, waiting to catch a single proton in the act of dying. So far, it has seen nothing. This tells us that if the proton decays at all, its average lifetime must be staggeringly long, far longer than 10 to the 34th power years, vastly longer than the present age of the universe. Whether it decays on even longer timescales, or whether it truly lasts forever, the honest answer is that nobody knows. It is one of the great unanswered questions about the deep future of reality. If protons do decay, then the degenerate era ends with the slow dissolution of all ordinary matter. Across spans of time measured in those almost unwritable numbers, the white dwarfs and neutron stars and cold dead planets simply evaporate from within, their protons decaying one by one, the solid matter of the universe melting away into a thin drift of radiation and stray particles. The cinders of the stars do not merely go cold, they cease to exist as matter at all, and then comes the black hole era. With the stars long dead and ordinary matter dissolved, the only substantial objects left in the universe are the black holes. They are the last great structures, the final islands in an ocean of almost perfect emptiness. For a span of time that dwarfs everything that came before, the universe belongs to them, but they too are living on borrowed time, leaking their mass away through that faint Hawking glow, growing slowly lighter across the eons. The smaller ones evaporate first. The largest ones endure to the very end, the last warm things in an otherwise frozen cosmos. And then, after that google of years, After a span of time that makes the entire age of stars look like a single struck match in an endless night, the last black hole releases its final burst of radiation and is gone. What remains is the dark era, the final age, and the longest of all, because it has no end. By now the universe holds no stars, no planets, no black holes, no atoms. There is only an unimaginably thin scattering of the most stable leftover particles, drifting through a space that has expanded so enormously that any two particles are separated by distances the mind cannot frame. And because of dark energy, because of that strange repulsive push woven into the fabric of empty space, the expansion never stops. The particles drift ever farther apart, into ever deeper cold and dark, forever. There are no more events. There is no more change. There is only an endless, silent, expanding emptiness, growing colder than cold, for all of time that remains. There is another possibility, darker and faster, and it too must be treated as the speculation it is. If dark energy is not constant, if it grows stronger over time rather than holding steady, then the universe faces a very different ending. In 2003, a physicist named Robert Caldwell explored a scenario that has come to be called the Big Rip. In this version of the future, the repulsive push does not merely separate the galaxies, it strengthens without limit. First it tears the clusters of galaxies apart. Then, billions of years later, it rips apart individual galaxies, scattering their stars. Then, in the final frantic moments, it overwhelms gravity even at the smallest scales, tearing apart solar systems, then planets, then atoms themselves. The push finally and completely defeating the pull, the fabric of space expanding so violently that nothing bound can survive. Whether the universe ends this way, in a sudden tearing, or in the slow eternal cold of the dark era, depends on the precise nature of dark energy. And the precise nature of dark energy is something we do not yet understand. Step back, now, from these vast and frozen futures, and notice what they all have in common. In every version of the end, the two faces of gravity are present, and they are in opposition. The one-way pull, the force that gathers, the force that built the galaxies and lit the stars and assembled the atoms of your body, is the force of the past and of the present. It is the great creator. It drew the formless gas of the early universe into structure, into warmth, into the conditions that made life possible. But across the immensity of the future, it is the push that wins. The expansion of space, driven by that faint repulsive energy hidden in the vacuum, separates and scatters and dilutes, until everything the pull once gathered is pulled apart by distance, or torn apart by force, or simply left to drift alone in an emptiness without end. Creation belongs to the pull, the long, cold future belongs to the push. And there is a strange mercy in the timescales. The universe does not hurry toward its ending. The numbers are so large, the eras so long, that the entire history of stars and planets and life occupies only the briefest, brightest sliver at the very beginning of time. But the expansion that empties the sky carries a quieter consequence with it, one of the most haunting ideas in all of cosmology. As space stretches, the most distant galaxies are swept away from us faster and faster, their light reddened and dimmed until, in the far future, they will slip entirely beyond the reach of any telescope that could ever be built. The faint afterglow of the universe's birth, the radiation that fills the whole sky tonight and lets us read how everything began, will itself be stretched until it fades below all detection. A civilization arising in that distant age, gazing outward, would see only its own island of stars adrift in an endless and featureless black. They would find no evidence that anything else had ever existed. They would have no way to know that the cosmos was once dense and hot and brilliant with light, no way to discover that space itself is expanding. They would conclude, reasonably and entirely wrongly, that they lived in a small and static and eternal universe. The truth that we can still just barely read in the sky, the truth of the great expansion, will one day be erased by the very expansion it describes. We do not only live in the age of light, we live in the narrow window when the universe can still be understood. There is one more truth to sit with before the end, and it is perhaps the strangest of all. After everything we have traced tonight, after the centuries of careful work, after the equations that predict the heavens to staggering precision, we must admit something that physicists do not always say aloud. We do not fully understand gravity, the oldest force we ever noticed, the first one any child feels, the one that has shaped this entire long story, is in truth the one force we understand least at its very foundations. Here is the problem. We have, today, two great theories of how the universe works, and each of them is among the most successful ideas in the history of human thought. The first is the theory of gravity that Einstein gave us, the picture of smooth, continuous, curving spacetime. It describes the large world with breathtaking accuracy. It predicts the orbits of planets, the bending of starlight, the ticking of clocks, the merger of black holes, and it has never once been found wrong. The second is quantum mechanics, the theory of the very small, which describes everything else, the behavior of particles, the forces between them, the discrete and probabilistic flickering of the subatomic world. It too has never been found wrong. Between them, these two theories describe nearly everything we have ever observed. The trouble is that they cannot both be the whole truth, because they do not fit together. They are built on different foundations, and they contradict one another at the deepest level. Gravity, in Einstein's picture, is smooth and continuous, a gently curving sheet. The quantum world is grainy and discrete and uncertain, forever jittering. And when physicists try to force the two to agree, when they try to describe gravity itself in the language of quantum mechanics, the equations break down. They produce infinities. They give answers that are not merely wrong, but meaningless, nonsense pouring out of the mathematics where sensible numbers should be. The two greatest theories we possess refuse to speak the same language. For most of the universe, this does not matter, because the two theories rule different domains. Gravity dominates the large and the heavy. Quantum mechanics dominates the small and the light. They rarely meet, but there are two places in all of reality where the large and the small collide, where matter is crushed so densely that gravity becomes overwhelming at the very same scale where quantum effects rule. One of those places is the singularity at the heart of a black hole. The other is the first instant of the universe itself, the beginning of everything. In both of those places, both theories apply at once, and both theories fail at once. We do not know what happens at the center of a black hole. We do not know what happened in the first unimaginable fraction of the first second. At the two most extreme moments in all of physics, the moments that bracket existence itself, our understanding simply runs out. The honest answer, the only honest answer, is that nobody knows. Einstein himself spent the last 3 decades of his life chasing a deeper theory that would heal this rift, that would unite gravity with the rest of physics into a single seamless whole. He worked on it at the Institute for Advanced Study in Princeton, year after year, filling pages with equations, and he died in 1955 without ever finding it. A century later, we are still searching. There are candidate ideas, and they are beautiful, and they are deeply uncertain. One of them, called string theory, imagines that the most fundamental things in the universe are not point particles at all, but tiny vibrating strings, and that the elusive carrier of gravity emerges naturally from their music. Another, called loop quantum gravity, imagines that space itself is not smooth, but woven from minuscule discrete grains, far smaller than any particle. Both are serious attempts by serious minds. Neither has ever been confirmed by a single experiment. We do not know if either is correct. We do not know if the true answer is something no one has yet imagined. And so the force we have followed across this entire long night, from the bed beneath you to the edge of a black hole to the cold and distant end of time, remains at its very deepest level a mystery. We can describe what it does with almost perfect precision. We cannot yet say what it truly is. There is something fitting in that, something that belongs to the quiet of the hour. The first thing we ever felt is the last thing we will fully understand. So we return, at the end, to the question we began with. Why does gravity only pull and never push? We have traced the answer through the weakness of the force and the strange fact that it has only one sign, through the curvature of space-time and the bending of light and the slowing of time, through the accelerating expansion and the dark energy that is the closest thing the universe has to a true and lasting push, through the even-numbered spin of a particle that has never been seen, and the antimatter that falls downward like everything else, and the collapse of stars into objects from which not even light can climb free. We have followed the one-way pull from the gentlest warmth to the most violent dark. And now, in the quiet, there is one last thing left to consider, which is not a fact about gravity at all, but a question about what it means to live inside its grip. Perhaps the one-way pull is the universe's single act of generosity. Perhaps it is the kindest thing about reality, the one force that refuses to let matter stay scattered and cold and alone. Every other tendency in nature seems to pull things apart. Heat spreads out and dissipates. Order decays into disorder. The expansion of space carries everything away from everything else. In a cosmos that seems forever bent on separation and cooling and forgetting, gravity alone insists on gathering. It is the force that drew the formless gas of the early universe into the first dim stars. It is the force that built the worlds and held the oceans to them, and kept the air from drifting off into the void. It is the reason there is something here, in this place, instead of a thin and even fog spread across an empty sky. Perhaps the fact that gravity only pulls is the reason there is anything at all worth talking about, including the two of us, here, now, thinking about it together. Or perhaps the one-way pull is the universe's single inescapable verdict. Perhaps it is the most unforgiving thing about reality, the one force you can never turn off, never block, never hide from, never outrun. You can shield yourself from every other force in nature. You can cancel an electric field, deflect a magnet, build a wall against the wind. But there is no wall against gravity, no shadow it does not reach, no corner of the cosmos where its pull does not extend. It bends the path of light, it slows the passage of time. It waits, patient and certain, at the bottom of every collapse, and when matter gathers densely enough, it permits no escape and accepts no resistance, folding space itself shut around whatever falls in. The same force that gently holds you also rules the place where physics ends and our equations fall silent. Perhaps the fact that gravity only pulls is not a kindness at all, but the quiet and absolute authority beneath everything, the one law that never relents. These two readings sit side by side, and physics cannot choose between them. This is the thing worth understanding about the science we have traced through this long night. Physics can tell us with breathtaking precision what gravity does. It can predict the fall of an apple and the orbit of a planet and the merger of two black holes a billion light years away, and it can be proven right to a degree of accuracy that staggers the imagination. But physics cannot tell us what gravity means. It cannot tell us whether the one-way pull is a gift or a sentence, a comfort or a warning. That is not a question equations can answer. That is a question that each person must answer alone, in the quiet, for themselves. Whether you find the inescapable gathering of all things a reason for peace or a reason for unease is not written in the mathematics. It is written, if it is written anywhere, only in you. And so consider, one last time, the scale of the thing you are a part of. You are lying or sitting somewhere on the surface of a single rocky world, held gently in place by the pull we have spent this night trying to understand. That world circles an ordinary star, one of several 100 billion stars in a galaxy so wide that light, the fastest thing there is, takes 100,000 years to cross it. That galaxy is one of perhaps 2 trillion galaxies scattered across the observable universe. And the observable universe itself, the sphere of everything we could ever in principle see, stretches roughly 93 billion light years from one side to the other. Within that sphere there are more stars than there are grains of sand on every beach and in every desert on Earth. And every one of those stars, and every world that circles them, and every wisp of gas that will someday become a star, is governed by the same silent rule that holds you to your bed tonight. One force, one direction, one unbroken law, reaching across a span so vast that the light from its farthest edges has been travelling toward us since long before the Earth existed. Against that scale, you are almost nothing, a single small gathering of atoms on a thin crust of rock around one dim star at the edge of one ordinary galaxy in an unremarkable corner of a cosmos so large that the entire Earth and everything that has ever happened on it is less than a mote of dust adrift in an ocean without shores. It would be easy, holding that thought, to feel crushed by it, to feel that nothing here could possibly matter against a backdrop so immense and so indifferent. But there is another way to hold it, and it is just as true. You are not separate from that vast cosmos. You are made of it. The atoms in your body were forged inside ancient stars, gathered together by the very pull we have been tracing, assembled across billions of years into something that can lie awake at night and wonder why gravity only pulls. You are not a stranger looking in at the universe from the outside. You are a piece of the universe that has arranged itself, however briefly, into a form that can look back at the whole and try to understand it. The same one-way pull that gathers galaxies gathered the matter that became you. You are, in the most literal sense the words can carry, a child of attraction. Everything you have ever loved, every face you have ever held in your memory, every warm and ordinary moment of your life, exists because gravity refused to let the matter of the early universe drift apart into nothing. That is the strange comfort hidden inside all of this dread. The universe is vast and cold and almost entirely empty, and it is running slowly down toward a darkness that will last almost forever. All of that is true. But you are here, now, in the brief and brilliant dawn of time, while the stars are still lit and the gathering is still going on. You were drawn together by the oldest force there is, the one that builds before it ever destroys, the one that gave you a world to stand on, and a sky to look up into, and a body warm enough to feel the pull that holds it down. The collapse comes for everything, eventually. The push will win, in the end, across spans of time too long to fear. But the end is not yet. The end is not for an almost endless while. And the end is not here, in this room, on this small warm world, tonight. So let the weight settle over you, the way it always has, the way it always will. Feel the gentle, constant pull that holds you to the surface of the Earth, the same pull that holds the moon in its orbit, and the Earth around the sun, and the sun within the slow turning of the galaxy. It is the weakest force in all of nature, and it is the one that shapes everything. It only ever pulls, and never pushes, and because of that single strange fact, there are stars and worlds and you. There is no escaping it, and there is no need to. It is not a sentence and it is not a gift. It is simply the deepest law of the place we find ourselves in, holding us, as it holds everything, toward everything else. Forever. Gravity will gather all things, and gravity will let all things go, across more time than the mind can hold. But not tonight. Tonight, on this small warm world,